Great. Hello, everybody. Welcome. Thank you all for being on time, and we're super excited to get started talking about this topic with you. While we're waiting for everyone to join, while we're kind of kicking things off, we'd love for you to utilize our little Menti question. We just want to kind of get an idea from everybody who's joining today. Sort of how familiar are you with this process, this concept, this tool, pinch analysis? How familiar are you with this? And there's in the Menti, you should have a bit of a rating scale where you can rate yourself on your familiarity with the topic, so that our experts today and myself have some sense of your experience right when we get started off. So please utilize that. You can also click the link that Kobe has dropped into the chat if you want to access it that way, or you can scan the QR code using your phone. You can also go to menti.com and put in the code 83835635 to answer that question as well. And we're going to get started pretty quickly here so that we make sure we have lots of time for questions and make sure we cover all of our great subject matter here. But we'll give you maybe about a minute more to answer that Menti question. If you do have any trouble with the Menti, feel free to type in the chat as well, and you can just let us know in the chat as well. Great. So let's take a look at what we're seeing for our results here. Okay, this is super interesting. um, Looks like we've got about 6 replies so far from our audience. And we're sort of, it looks like we're hovering around a 3.5 familiarity. So we're rating here all the way from I have no concept of it to I have conducted a pinch analysis. So I think probably Emily and Nafel, you guys didn't put in your answer, which is the right thing to do. But we have some okay experience or some okay knowledge of this, which is great. Okay, so let's go ahead and get started. My name is Amanda. I'm super excited to be presenting on behalf of Save On Energy today on this topic of pinch analysis. And we're really just looking to kind of demystify this concept to understand a bit more about where the opportunities might lie for you and your organization. And we'll have a chance to meet Emily and Nafel a little bit more, but I just want to welcome them here today. They're going to be talking with us and sharing their expertise. And then we also have Asia joining us from the IESO. And Asia, I'd actually like to pass it over to you at this time, because I know you have a bit of announcement for this crew today. So I'm going to stop sharing and I'm going to let you go ahead and share your screen and tell us a little more about what you're sharing.
Thanks so much, Amanda. It's really exciting to be here. I'm excited for this topic and to learn about pinch analysis. I'm just going to take us very briefly through some of our program offerings that you may or may not be familiar with, just about 5 minutes here to make sure that you have access to this information. Is everyone able to see my screen? Great. So just a brief overview here of our Save On Energy offerings. You can see we have programs that are available to all businesses, to medium and large business and small business. I'm going to go over the all business and medium large business at a high level, and you will receive a copy of the slide deck after the training. So you will have this information to refer to. Just want to talk a little bit about our existing building commissioning program that helps your building get back to working the way it was originally intended. So this is a 3-step process, this program, which involves hiring a commissioning agent to help you identify projects and activities that can support you in commissioning your building. There's, you can see on the screen, there's some information about the electricity use that is required to be eligible, and you can receive incentives up to $150,000. You may also be familiar with our energy performance program. So this program is a performance-based incentive and is calculated on a baseline energy consumption with incentives paid over 3 years. And these incentives are 15 cents per kilowatt hour for electricity savings during summer peak hours and 4 cents per kilowatt hour for off-peak. This is a program that can really support you in terms of incentivizing those gains over your baseline. As well, in June, we announced some improvements to our retrofit program. So if you're interested in changing or upgrading equipment, this program offers 50% up to 50% of eligible project costs, and there's a prescriptive and a custom stream. Some of the key measures are variable speed drives, compressed air motors, but there's a wide range of measures and upgrades that can be eligible within this program. And one of the biggest enhancements to the retrofit program this year is the expansion of incentives for solar PV across the province. There was a pilot done in Ottawa last year, and we've now expanded it. So there's also up to 50% of eligible project costs for this incentive with 2 types of projects, depending on scale there that may be of interest to you. Our instant discounts program, these are point of sale, no paperwork for lighting. So you go to a participating distributor that can be found on our website, and there's over 500 of them across the province. If you have lighting upgrades to make, this could be an excellent opportunity. We also have our expanded energy management program. So this program is offered with financial support from NRCan's Green Industrial Facilities and Manufacturing Program for our industrial customers. And it offers energy manager support, so energy manager funding, strategic energy management cohorts with associated performance incentives, as well as energy management information systems. On the industrial side, the energy manager and strategic energy management offerings are pretty much at full subscription. We're looking at ways to add additional participants. So please express your interest to us if you're interested in that. And the energy management information systems, if you're working on your energy management, your building automation, different things that you're looking to get more data out of your facility to make decisions, it's a great offering, something you might want to think about today. And finally, I just want to take a moment to talk about our industrial energy efficiency program. So we have a new program. It will be launching soon, and more information will become available. However, these are some of the improvements that are being incorporated through extensive stakeholder engagement sessions. So some of the things we heard, this is the program that will be replacing IEP, if you're familiar with that one. So we will be making the application process easier, single sign-off, first come, first served. The cap has been raised quite significantly from 5 million to 15 million per project, with the possibility of more. The completion window has been extended from 3 to 5 years. And we also will be offering feasibility study funding. There's a lower threshold for eligibility, 600 megawatt hours per year. And there is NMV support for your measurement and verification activities. So stay tuned for that. That will be officially launching soon. And I'll just pause briefly on this slide. If you have your phone, you can take a photo or use the QR code to sign up for our newsletter. Again, you'll have this information after the session. If any of those programs interest you or you're not sure where to start, please reach out to us at save@energy@iso.ca. And now back to
Excellent.
topic of the day.
Yeah, thank you so much for those updates. Always great to have you come and share all the newest program developments. Excellent. So let's move things back over to talking about pinch analysis. I just want to mention that we have developed a workbook for you on this topic. So it has some kind of key terms outlined. There's reference material. There's a bit of a screening exercise that we're going to talk about, and also some case studies. So you can use this workbook, and Kobe is going to drop a link for it into the chat. You can use it to take notes, kind of follow along, filling out information as we go through all the content today. We will reference kind of when to refer to the workbook, and I would recommend that you download it and you actually save a copy for yourself. So if you download it, you'll be able to edit and save that for your future reference. Also, just on kind of participation and this being a workshop, we hope that you will sort of participate in the activities today actively. We encourage the use of your camera if you're comfortable, especially during the Q&A. Maybe we can have a look, see who we're talking to today. Also utilize the chat functions and feel free to, contribute to the discussion. So this is meant to be really interactive, and it's all about making it work for you and getting the most out of it for you. So we encourage that sort of participation. So our main priorities for today are to share the benefits of conducting a pinch analysis, also to help you determine if a pinch analysis is really right for you and your facility. And we'll also help you identify some next steps you might want to take if you decide to proceed with a pinch analysis in the future. So those are our main sort of learning objectives for today. And at this stage, I'd like to take the opportunity to introduce more formally Emily and Nafel as our pinch analysis experts. And I want to give them an opportunity to each share a little bit about themselves and their experience on this subject. So maybe Emily, we can start with you if you want to say a little bit about yourself and your background.
Sure. Thank you so much, Amanda, and happy to be here for this pinch analysis training. So yeah, my name is Emily Thorne-Corte. I run Thorne Associates. Thorne Associates is a boutique industrial energy efficiency and decarbonization consulting firm. So we are niche. We focus exclusively on those topics, energy efficiency / renewable energy and decarbonization. We've had, I guess, my personal background over 20 years of experience in this field, an engineer by training, master's in mechanical engineering, and have had the opportunity to work not only with many industrial facilities on various energy and climate projects, including pinch analysis, and heat recovery and many other sort of climate and energy efficiency related subjects, such as energy audits and greenhouse gas inventories, energy management information systems, strategy. We work with board of directors, et cetera. And yeah, won a few awards too. So really happy to be here and look forward to diving into pinch analysis. And I'll turn it over to my colleague, Nafel.
Good morning to all. Probably good afternoon to some. So my name is Nafel Bouzayani, and I have close to 20 years experience in energy efficiency, heat recovery, energy optimization, and renewable energy as well. My background is industrial mechanical engineering with a master's degree in mechanical engineering. And through this close to 20 years, I have been doing mostly energy efficiency, energy optimization, heat recovery in mostly industrial sites, trying to help big organizations saving energy and greenhouse gas emission reduction, and in many fields, like including pulp and paper, cardboard, even like institutional, dairy, food and beverage, and so on. And I pass it now to Amanda. Thank you.
Great. Yeah, I mean, we have a wealth of expertise here, so definitely excited to hear more from both of you. And on the note of sort of expertise and sharing that expertise, I just want to note that you can utilize the Q&A function of this meeting. So in the top tab, you should have a Q&A button. And here will be a great place as a repository for your questions. So we're going to aim to answer any questions that are really pertinent to kind of the current subject live and as they come up. But for any questions that maybe aren't as related to the topic that we're discussing in the moment, we're going to pin them and come back to them at the end when we're going to try to save about 10 minutes to sort of answer those other questions. And I think we did actually have a question right at the beginning for Asia, and it was regarding the program, if it's only applicable to Quebec or if it's for other provinces as well. So maybe, oh, it looks like we got a comment. So Asia answered that. So maybe just for everyone, so you have that. All Save on Energy programs require the participant to be connected to the Ontario grid and for Ontario customers. So that's a demonstration of how the question and answer works. You can throw it into the chat or you can put it into the Q&A, and we will either address it as we're going along or we will come back to it at the end in the Q&A. Okay, so let's kind of get things started. So we started with a bit of a question on your experience with pinch analysis, but I'd like to understand a little bit more about what exactly you're dealing with in the way of hot processes and cold processes. And we're calling this icebreaker hot side versus cold side. So what we would like to see is utilize the chat function. So again, at the top of your screen, there should be a button for chat. And I want you to go into the chat, and if you click on the little emoji button, which is the smiling face, you can search for snowflake or fire or flame, and you will get essentially a snowflake or a fire or flame. So we want to see in the chat populated, what do you interact with more or most at your facility? Are you interacting more with cold processes, or are you interacting more with hot processes or heating processes? So please participate. We'd love to see sort of what folks are mostly dealing with here within their facilities. I'm already starting to see some responses come through. Okay, so we've got Doran is interacting more with hot processes, Tyler more with hot processes. Everyone's on fire, it looks like. Dave also hot processes. We have Andrew interacting more with hot processes as well. Okay, so definitely I'm seeing a lot on the hot side, not as much on the cooling side, which is quite interesting. But I think we'll get a little more information in the sort of second step of this process. So Emily and Nafel, you get some insights here. We're dealing with folks that are dealing mostly with hot processes in their facilities. So to get a little more detailed here, and I think we have a bit of a challenge with our annotate in this meeting. So we're not able to use the annotate as we originally intended, which is where we wanted you to actually write right onto the screen what processes or systems you're actually dealing with on the heating and cooling side. But maybe we can have that actually in the chat, or if you're willing to unmute and share with us, you can just unmute and tell us what are those processes and systems related to heating and cooling that you're currently interacting with or that you currently have at your facility. So please let us know in the chat what systems you're currently working with in a little more detail. And we'll give it a moment. If anyone is willing to, we'd also love to hear from you. And maybe while we're waiting for the chat to be populated, maybe I can call on someone. Andrew, maybe I can call on you. I see you just you just plugged something in.
Yeah.
Okay.
I didn't want to, take it away from others, but so I put some things in the chat. But yeah, hot processes that I deal with include sanitation with hot water, drying of various different types of products to drive off moisture or cure, and then log conditioning sometimes in the forestry products work that I work with. There's like frozen logs in the winter, and they've got to get them soggy actually. So there's a lot of heating there. Oh yeah, I see boilers in Doran's comment. That's definitely a big one. And then kilns as well, also for drying things.
Yeah, we see heat exchangers, steam and condensate systems, furnaces, incinerators. Yeah, no examples yet of cooling systems, but maybe I can just check in with our experts here, either Nawfal or Emily. Are there any examples of cooling systems that you can think of that might be common in these types of facilities? To put you on the spot a little bit, but yeah.
Yeah, sure. No, definitely like refrigeration if you're in, food and beverage, that could be a big one. Needing chilled water for various different processes. Also sometimes in flue gases of sort of something that needs to be heated, but actually the flue gases sometimes need to be cooled because of various constraints of materials or not needing, not having released to the atmosphere of dangerous sort of exhaust gases, etc. So those could be some examples. Cooling towers, someone mentioned for other various processes. So I don't know if Nawfal, you want to add anything? I think that there's not so much variation, I would say, with cooling. There's more probably variation with heating, but yeah.
Heating, yeah, for sure. No, it looks like we did get some examples in the chat. Yeah, Nawfal, if there's anything you want to add for cooling.
If I add, I mean, like the condensers as well. I mean, like the condensers in power plants or like out of the turbines, and definitely some clients or some industries, they have mandatory cooling for hot streams before they reject them either to the rivers or even like to the exhaust. So it's like a mandatory cooling for a good source of hot, lack of heat.
Yeah.
And actually, I just thought of a couple more too. Sure. Compressors often need cooling. Sometimes that's water cooling, sometimes that's air cooling. But then also, in Nawfal was mentioning generators, right? So there's like jacket cooling on generators. The oil needs to be cooled. So that water then gets heated and can also be used as a heat source, but it does need to be cooled and needs to have that initial cooling. So that's where some good pairing can be done.
Excellent. Yeah. And what we really aimed to demonstrate with this is that, within your facilities, you're having these heating processes and cooling processes sometimes sort of running side by side, one sort of adding heat, one removing it. And pinch analysis is really all about kind of connecting these dots so we can stop wasting energy, right? So really trying to kind of connect this together. So I'm going to take time here to we're going to pass it right over to Emily on our next slide. And Emily's really going to dive a bit deeper into what actually is pinch analysis.
So thank you very much, Amanda. So we're getting right into the heart of this. This is going from very high level, easy to kind of dive into a pretty complex slide. So I'm going to try and break this down for you step by step, and we'll spend quite a few minutes here because this is really sort of the core and crux of pinch analysis. So what is pinch analysis? We've defined it as a systematic method for heat integration and energy recovery at facility scale. So let's break that down. So first of all, systematic method. So there is a detailed methodology that is followed for pinch analysis. In today's session, this is more of a very high-level introductory session to pinch analysis, so we're not going to go through all the steps of the approach and methodology for actually how to conduct one because it is quite complex. However, as Amanda mentioned, you'll get to know whether your facility is a good candidate or not, so that you could perhaps take some further training or a consultant to help you go through this methodology. But it is systematic. The other part is it's at facility scale, so it's holistic. We're not looking at just one sort of small system. We're looking at a systems thinking at the facility scale. So it's not about just identifying, oh yeah, okay, we have this process that is releasing heat and this one needs to be cooled and we just combine the two, just very simple. No, that's not what we're looking at here. We're looking at all of what we call hot streams, which are heat sources or streams that need to be cooled, and all of the cold streams, which are heat sinks and need to be heated. We're looking at all of those together at the facility level and looking at both heating and cooling. So I did see, your responses about all heating. I think that is good in the sense of mostly heating, that a lot of the value in terms of economics, there's often a very large cost to heating, especially for very high temperatures and pressures. Hopefully you do have some cooling needs too, because the idea is to pair those. So that's kind of the high level definition. Pinch analysis is also sort of, I guess, a subset of process integration. So if you see anywhere, about process integration, then I would say pinch analysis is kind of a subset of that, and is really trying to integrate your process, but just on the sort of heating and cooling aspects of the process as best as possible. And one of the major benefits of pinch analysis as compared to, say, an energy audit is that pinch analysis will actually provide you fairly early on in the process the minimum amount of external heating and the minimum amount of theoretical cooling in terms of utilities that are required. So that is really important, because if you think, we've done many energy audits, and when you go in an energy audit, there is a methodology, right? For industrial, less so, but there are some standard methodologies that you can follow. But they don't give you typically a minimum amount of energy. You're just trying to get as many energy savings at an economically viable option as much as possible. But with pinch analysis, you actually get that theoretical minimum. Now, of course, in practice, you're not going to attain a theoretical, but it's still really useful to know what that theoretical minimum is, because then you can see from a practical perspective, how close you can get to that. And in terms of this graph here that you see on this slide, you can see actually, I just realized, because I guess I can't use the laser. I just realized, Amanda, because you're presenting. Can I? Or
yeah, is it helpful for me to go to the next slide, which zeroes in a little bit more on the graph, or maybe hold tight yet?
Let's hold tight. But anyways, okay. If you can see on the light blue arrow that has QC labeled, that is the cold utility, external cold utility. So that would be typically chilled water, cold water that you'd need in the minimum amount if this has been an optimized process. And then on the right hand side, the QH, the red arrow, then that would be the minimum amount of hot utility, often, for example, steam or hot water needed. So that's a really important part of the process, is to get that minimum. Then what you're seeing on this graph, it's a temperature versus enthalpy. Enthalpy is the heat content of a fluid, are what are called composite curves. So the orange line is a series of hot composite curves. So again, hot being, it's maybe a little counterintuitive, hot being a heat source, meaning it needs to be cooled, and cold in the blue curve is a cold composite curve, and it's made up of a number of cold streams. And this enables us to visualize the heat flows that are occurring across the whole facility. And I'll go into more detail in the next slide on that, but a few more points first. So you can also see this, these hot and cold composite curves have what's called a pinch point in the middle. And the pinch point, as you can see in the red sort of bubble, is at the delta T min, or like sort of where the hot composite curve is the closest point from the hot composite curve to the cold composite curve. In this case, it's about 20 degrees C from, if you look at that point in the middle, 80 to 60, it's a delta T min of 20. And I'll get into, there's different, when you design the heat exchanger network, you can see the implications of changing that delta T min, which basically can drive the minimum utility target. So by changing the delta T min, you're going to change that theoretical minimum of the cold utility and hot utility required. So once you have developed this, which you use, by the way, through software, then so once you've developed the hot and the cold composite curves by basically taking all the information from all the hot and cold streams in your facility, then it enables you to do a strategic design of a heat exchanger network. And I'm guessing that most of you are in a operating current, like a facility that's currently operating, as opposed to, design of a new facility. So in a operating facility, it's a retrofit situation. So you'd actually basically display in the software your current heat exchanger network, and then in a second phase, you would use the software to optimize and develop a more efficient heat exchanger network. And then finally, you would prioritize investments. And the software does provide some high-level capital costs, so for the heat exchangers, piping, etc. But I do want to stress that these are very conceptual, high-level numbers that you're going to get out of any of the pinch analysis software that's available on the market. And there are a number of them. I'll just say, like, integration, I would probably be the one that I would, this is not an IESO recommendation, this is me personally, just sort of saying the integration software is from Enercan. And so I think it's a Canadian-made, great software, similar to, well, similar that RedScreen's Canadian made, and high quality, I think integration is as well. And so that would be one I recommend. There are some free pinch analysis software available as well, and others out of Europe and elsewhere. But essentially, you do need to do a feasibility study afterwards. You would want to get, vendor quotations, etc., after doing the pinch analysis before proceeding. So that is a lot. Just give me 1 second to see if there's anything. Oh yeah, I missed before we move to the next slide. There is one other thing. There's some golden rules when you develop your pinch analysis, that you don't want to, for example, have any external heating below the pinch point, because you're just supposed to have that external cooling. And similarly, above the pinch point, you do not want to have any external cooling, because you're only supposed to have that hot utility, because if you do that, it'll lead to inefficient heat exchange. And similar, there's a third golden rule about no heat exchange between streams across the pinch point. So there's those three golden rules that need to be used and applied, again, sort of relying on the software for that. So let's go to the next slide and get a bit of a deeper dive into these streams, and then maybe I'll pause because I know this is a lot to take in. So if we look at the hot composite curve, so that orange line, so there are actually 5 different streams in this facility, hot streams in this facility, and you can tell that because if you look at the dots, in the dots are sort of the boundaries of the stream. So the first stream, if you think about it, if you took at the top right, and you're at 180 degrees Celsius, you can see that first stream, and it's going down to 140 degrees Celsius. So this is a hot stream that needs to be cooled from 180 to 140. In the process, it's going to lose some of its heat content, hence the enthalpy is going more from the right to the left. This second stream is starting at 140, and it needs to be cooled to about 80 degrees Celsius. And then so on, right? And then you have another sort of stream that is only going from 80 to about 70, and then et cetera. So you have about 5 hot streams that are in your hot composite curve. And then sort of similarly, the cold composite curve, now we start on the bottom left. So the cold composite curve, the coldest stream is at around 30 degrees Celsius, and it is moving up to around, it has to be heated to around 60 degrees Celsius. And then you can actually see there's only 3 cold streams here. So you do not necessarily have to have, you definitely, I would say, you typically do not have the same number of hot and cold streams. But what's important is you want to kind of maximize that green curve at the top, the Q recovery. That is the width of that represents where there's heat exchange going between a hot stream and a cold stream. And you want to maximize that as much as possible, and your choice of delta T min will affect how long that, sort of how wide that bar is. And the wider it is, the more heat recovery you're going to have, because you can see under the QC, if you look at under the QC, there's no cooling streams to help cool the hot streams. That's why you need that cold utility. And then similarly on the right-hand side, there's no hot streams to heat the cold utilities on the QH area. So that's why you have a hot utility. I do see a question. Just want to finish up this slide, and then I'll pause. So if we just kind of think of an example in real life, or like that, will imagine a chemical plant. So there's a tank of chemicals that need to be heated. They're currently heated by steam from boilers. So what type of stream would the chemical be they're currently, the tank of heat needs to be heated and they're currently heated by steam from boilers? Any thoughts? You can just type it in the chat maybe.
Yep, feel free to unmute and answer. Oh, Andrew is
Blue stream, yes. Oh, sorry, yeah, cold.
Excellent.
Yeah,
Cold
exactly,
stream.
cold
Perfect.
stream. And then now there's also a drying furnace whose hot flue gas is cooled by cold water from cooling towers and then exhausted to the atmosphere. So what type of stream would the flue gas be? Hot, good, yes, a hot stream, or in this case, orange. Excellent. Okay, so you've got the idea of hot and cold streams. So instead of using a separate cold utility, such as cold water from the cooling towers for the hot stream, and using a hot utility like the boilers and steam for the chemicals, then we can design a heat exchanger where the chemicals tank is heated using an indirect heat exchanger with the flue gas, resulting in less steam, aka less of the hot utility being used, and less cooling water, leading to big energy savings. Now that's just one example, but with the software, you'd actually optimize all the heat exchangers one after the other, sort of holistically and together. And by the way, there is again a methodology. So you actually start with the heat exchangers that are closest to the pinch point, and then you work outwards from there. So now that was what I wanted to cover on this slide. So I'll go back to Andrew for the question.
Yeah, thanks. So if I'm understanding this right, each of these curves is just representing one fluid that goes through different stages. I could imagine a facility, and I guess it's like those two, the hot and the cold fluids are the things where you're considering doing a heat exchange between them. But I can imagine a facility that's got lots of cold curves and lots of hot curves because they have different processes with different fluids or different fluids in the same process. Like, is it ever useful, or does it just get confusing if you try to chart more than two fluids? Like you say you had two hot streams and two cold streams on the same chart, or would you just not do that because you're really only considering one heat exchange for each chart you make?
I'm not sure I fully understood your question, Andrew. So you're saying that you're wondering, can you just repeat the end part of that?
Yeah, I mean, so is it clear what I'm saying? Like, you know, okay, so you gave the example in the cold stream of steam that needs to be cooled down, but you might also have water in the same facility that goes through a cooling. So those would be different different curves, right?
So sorry, go ahead.
Go ahead. Yeah.
No, so if you have utilities, so you could have multiple cold utilities and multiple hot utilities. So you could have a cold water utility and a chilled water utility, and those can be managed, yeah, holistically. So I would say, I think if I'm understanding your question correctly, is you can put on all the curves. Like you basically, I mean, we're dealing with a facility right now. It has 45 streams. So I think I'm trying to remember if that was hot and cold or just hot, but you know, it's a lot, right? So this is a simple example, but in reality, it can get quite complex, and there's a whole part of the methodology at the very beginning is called data extraction, and you have to take the process flow diagram and identify all of those streams essentially, and extracting that is a bit of a science and art, and there's actually some judgment there that can actually change the results. So I think the answer to your question, again, I'm still not fully understanding. Maybe Nawfal, you can jump in, but if you understand his question better. But I think the answer is that you know, all your streams would fall on this curve. You want to have only one hot composite curve and one cold composite curve for the whole facility, and they should all be on there.
Okay, yeah, that I mean, I would welcome more comment, but that does answer it. That's interesting.
Yeah. If I understood your question well, I mean, like those brackets for the temperature, the dots that you see on the curves, they're just the temperature change. If you class all the hot streams, let's say, together, so you start like from the coldest to the highest, and every time there is a change, so there is a combined portion of each stream between those two brackets. You know what I mean? So let's say from 40 to 60, you may have like one stream or one full stream and probably 25% of another stream. They're stuck all together. So those dots, they're just a change of the temperature range for all the streams.
Yeah, there could be. Yeah, there could be. I tried to simplify things to not get, but yeah, Nawfal's correct that you could have those. Those could be not just one stream, but there could be parts of another stream. I didn't really want to get into too much of the details.
Let's move on.
But,
we can talk about it another time because this is opening a whole lot of other questions for Rebecca because they're in the complexity that we may address. So okay, thanks.
Definitely for the sake of time, we'll save getting deeper into the possibilities of streams, and maybe I think, Emily, if you want to talk a little bit about this, why this is so important, why do we get into all this complexity in the first place?
Definitely. Well, the holistic aspect of energy management is really important because you're essentially going to have a higher amount of savings. So pinch analysis sort of studies have shown that typically you have a potential cost-effective energy savings of 10 to 35%. So you're getting way more, again, than say a typical energy audit, which may be in the 5 to 10%. So this is very substantial savings. Again, 10 to 35% is typical, which I think is way more than any other, again, energy audit or some other kind of energy efficiency intervention or even strategic energy management. Someone can correct me, but I don't think it gets up typically that high. So it reduces the total energy use by addressing the interstream interactions, not just isolated inefficiencies. Again, that system aspect cuts operating costs, again, by recovering waste heat, reducing fuel and electricity demand, and potentially deferring capital investment. And it guides investment priorities towards measures that maximize whole facility impacts rather than incremental component gains. So sometimes if you just look at one one component and say you want to swap out a pump or swap out a compressor or something like that, then that might not, it might have a worse impacts downstream if you don't look at it as a system basis. So that's what I'm a systems design engineer by background. I said I had a master's in mechanical, but my bachelor's is systems design engineer from Waterloo. And so I always like to think as a system, and I always think that is going to be you're going to get deeper, larger savings when you look at that. So I think we can move to the next slide. So, and maybe just mute someone who.
Yeah, I'm just finding them. Okay. So, oh, sorry. There we go.
Okay, perfect. So, yeah, this is just sort of showing the difference between, a traditional just equipment level isolated improvement upgrade versus the system level optimization. And I'll just this is a really simple example, but from maybe like 20 years ago, 25 years ago when I was starting my career, there was the transition going on from incandescent and fluorescent lighting to LEDs. And it wasn't a pinch analysis at that time, but I'm just using the example for, system level thinking, because what was happening at that time was at the early days, people were replacing their incandescents or fluorescents with LEDs. And then they were cold because they were used to having all that heat that was from the incandescents and fluorescents, and they actually found their heating bill went up, and they had not anticipated that in the business case. So that is just sort of a lack of systems thinking. I'll give a maybe more industrially relevant example with respect to one of our clients we started doing an energy design review with them. If you're not familiar with the energy design review, it's basically like an energy audit on paper for a new facility, like a green field that's not yet built. So And by the way, pinch analysis can be done. It's actually easier to be done for new facilities that are not yet built, i.e. in the design phase. So for this energy design review, we were tasked with finding the top 5 opportunities for energy efficiency and decarbonization, and 2 of the top 5 were heat recovery opportunities from a diesel generator. One to do heat recovery for electricity generation through an organic Rankine cycle, and the other for heat recovery for steam generation that'll offset standalone, hot utility, a steam boiler in this case that was fed by diesel because it's off the grid in a very remote location. We are, by the way, trying to get renewable electricity as much as possible, but they're like 400 kilometers away from the grid, so it's quite challenging. Anyways, the purpose of this is to say that we've done these sort of standalone analysis of the heat recovery for the diesel generator using hot and cold streams that are available, and it's going to be extremely economically attractive. But what we've actually suggested from doing this energy design review, we realized, which we didn't know earlier, is, hey, this is actually a really great candidate to do a full pinch analysis. They have a refinery, for example, and so that's what we're slated to do next year. And so I think that just shows sometimes, you dive in right to the systems level, but sometimes you can start with sort of that most lucrative, most attractive kind of heat recovery opportunity, and it can open your eyes to actually this is a really good candidate for a system level pinch analysis. So I think that is it for now for me, and I will turn it back over to you, Amanda.
Sure. So I think we're going to actually go right into some case study examples from NAWFL, just outlining sort of what this looks like in a case. In the meantime, maybe while NAWFL is just kicking things off, I'd love to hear in the chat, if you'd like to type in the chat, tell us maybe a little bit about what you're hoping pinch analysis might do for you at your facility. What are you looking to kind of get out of this? Are you looking for a sort of whole system level optimization? What is your sort of goal for starting to look into this? And so let's go over to NAWFL's case study, really digging into kind of the problem and how this was tackled.
Okay, so in fact, I'm representing a case that was done by Enercan, and specifically CanMet, which is like they did like a few case studies that they are published, and I did the choice to make it easy for all of you to see the full documentary. So it's the same department that it was involved in developing the software that Emily mentioned, which is the integration process integration. It's very easy and efficient software to be used. So the case that I'm gonna present, it's just for ammonia plant. For the ammonia plant, it's mainly, like with a capacity of 1,000 tons per day, and it's mainly reforming the fuel gas using steam. So it's very energy demanding, and the steam cost was high as well as the fuel. So it was definitely like figure out that there is significant heat losses from multiple processes, including the reformers, flue gas, some rejects, and so on, and definitely inefficient steam generation. So if I have to dip, the diagram it's a little bit complex. But if when you go to the document, so the input, which is where it's showing natural gas, it goes from the top left with the steam and air, where it gets like the reformation through many steps, like through cooling and heating up to 1200 degrees C, which is a lot, to produce ammonia mainly. And ammonia, it's used like in different multiple processes. So and that was done by the way in 2012. And as I said, like there is the full study that you can find online to have like all the step-by-step analysis. So the steps, in fact, like what they did, they define the hot streams and cold streams as Emily mentioned early on, and through that, so there was a definition. They defined the measured inefficiency, and the measured inefficiency it was including it's either heat losses or even like a system inefficiency. As an example, let's say the turbines. So they were trying to see if they can reduce the steam consumption in a turbine by making it like a more work efficient. And then, I mean, like, if I have, because, okay, so at the, I mean, as you can see in here, through the process, like starting from about like 200 to the end to the right to 1200, they added what you see in blue at the bottom with heat exchanger. So they were thinking about through the key integration, so to reduce the high pressure. So they were using a lot of high pressure and low pressure steam. So they were working towards reducing the high pressure steam because it's very costly, and trying to do some heat recovery, and mainly it's through the stack with about like a 12 megawatt of available heat. So probably if you go to the next. So the results through this study, as you can see, they are tremendous. So they were getting to about like 30 tons of 30 tons per hour of steam reduction, which is like mainly about like 20 megawatt of high pressure steam. And the energy savings, they were evaluated to 2 gigajoule per ton of ammonia. So the total cost savings, the annual cost savings, they were estimated to 3.8 back in 2012. It should be higher, much higher now. And there is about like 11% of NOx and carbon dioxide reduction. And with an estimated project cost back in 2012 of about $6 million, they calculated a simple payback period to 1.5. So by this project, they were assuming that they're gonna shut down the boilers. So there will be no boilers. It will be mainly just the steam, the packaged boiler. So yeah, that was really quick, and yeah. Just avoiding like getting in too much details.
Yeah, for sure. No, I mean, it's hard to reduce some of this complexity down to some bullet points, right? I think we can recognize that it is, but we wanted to share a few examples and ones that are readily available as well. So you can go to the NRCan site and sort of dig into these case studies in more detail for more if you're interested in that. I'd like to, I guess, have a little bit of a really quick chat because we want to keep things moving. But I'm wondering if anyone has kind of any thoughts related to what Emily was talking about as far as taking this kind of whole system approach and also looking at the case study. Do you think there might be some barriers, or what those barriers might be that would prevent a facility manager from adopting a kind of whole system approach and doing a pinch analysis in this manner? Would anyone like to comment on what might be kind of some of the barriers to taking this type of approach? Any thoughts on that? Yeah, Dave is mentioning in the chat just like the sheer kind of complexity of the system, and maybe not quite knowing where to get started or things like that. Yeah. For sure. Any other barriers? Lack of data. Yeah, Tyler, so maybe just having a lack of data that would drive those actions. Absolutely, definitely a barrier. Anything else that anyone might be able to identify? I think those are two really good ones. Retrofit of existing processes. Yeah. Do you I think that's Doran, retrofit of existing processes. Do you want to explain a little bit what you mean by that as a barrier, or maybe our experts also know? Or I think you've unmuted. I'll let you speak.
Yes, good morning. What I mean by this is trying to retrofit existing processes, and probably more complex would be to convince the production and the operating team that this is going to drive energy savings. So that's that friction between engineering, management versus production and operating groups.
Absolutely, that makes sense. I think Emily mentioned at the beginning, probably most of you are in facilities that are already operating versus getting to design kind of a fresh new system. So definitely that having to retrofit, having to look at existing processes and modify them versus getting to start from scratch would definitely be a barrier. Yeah, Emily.
Yeah, I just want to add, no one's mentioned cost, but as you can probably imagine, pinch analysis is fairly costly. And I will mention, I think towards the end, there is some incentive funding available from NRCan and other organizations. And so I think that can help with the cost, but as you can imagine, this is going to be more costly than just an energy audit because it's, but it does have more benefits too, right? So yeah, I'll turn it over to Nawfal if we have time, Amanda.
Yeah, for sure. Nawfal, do you want to add?
Yeah, in fact, like, thank you for sharing these points. In fact, like, if I start from the complexity of the system, that's really one of the biggest issues, because like in a complex, from, let's say, my experience in pulp and paper and other industries, you have to have like an overview of all the plant or the mill. So you have to involve multiple departments, and that's really, from one side, it's costly, plus it's really complex in the logistics. So that
it's a good point, I think.
Yeah, it is really one of the major barrier for this. And the second one, the lack of data, that's true. And the major thing, it's either like it's not available, or it's really difficult to get, or it's really costly to get. And definitely the retrofit, which is really, I think Emily mentioned that, which is mainly it's costly, but with the energy and with the energy cost that it's continue increasing, plus the carbon taxes and so on, it becomes like a very valuable solution.
I think those are really good points, and I'm excited. Actually, it's a great transition into kind of our next section, where we're going to talk about maybe some of the ways to overcome potentially some of these barriers to help you get started. So let's keep things moving, because I think we're running a little bit behind, so I may have to run quicker through some of these sections, but that's okay. We'll adjust. I wanted to kind of talk quickly about, looking at maybe some misconceptions, and Emily challenged me on this, and I thought it was very true, as a lot of folks don't have misconceptions about pinch analysis because maybe the knowledge is not quite there yet. So maybe not so much misconceptions, but wanted to kind of check in on what's true and maybe not true about pinch analysis from what we've heard so far. And maybe you can just put a true or a false in the chat, or a T or an F in the chat to these statements. So what is this, true or false? You can do pinch analysis in your head, and maybe after this discussion of complexity, this one is obvious. Yeah, Dave, definitely it's false. And then what about this one? Pinch analysis applies to one system or process. Any thoughts on this one? F, yes. Excellent. And this one, pinch analysis is too complicated to even start the process. What do you think? Too complicated to even start. This is a bit of a tricky one. It might be a little bit. Yeah, maybe. Yeah, excellent. So let's see what is true here. The reality is with this, you can do it in your head. As I think Emily and Nawfal have both mentioned at different points here, software modeling is really needed to help handle multiple streams when you're looking at a complex system. It only applies to one system. False also. It's really a whole facility integration method, which we really just heard all about from Emily. And it's too complicated. Also false. So there are screening tools, simple screening tools, and simple audits that can really serve to quickly flag what your opportunities are. And there are a list of references also in your workbook that you can utilize for some of these as well. So to kind of quickly illustrate some of these falsities, we took the case studies that were from NRCan to kind of unpack how they dealt with some of this. So this idea that you can do pinch analysis in your head, in the situation from the ammonia plant that Nawfal was discussing, in this case, the plant team sort of assumed that they had already optimized their process heat recovery, right? Especially around the reformer and waste heat boilers. They really thought that sort of intuition and these incremental improvements that they were making, they had optimized this. But when they did a structured pinch analysis, it uncovered essentially 11% additional energy savings that had been missed by kind of those assumptions that they were making. And the analysis really revealed that this kind of untapped potential in the process utility interface, not the process core, showing that this kind of mental accounting can't really capture that cross-system interaction. So the lesson here for everyone is that even experienced engineers can sometimes underestimate integration potential without quantitative composite curves and that data-driven targeting. So we know that data can be hard to get and these processes can be complex, but really important to do this modeling. And then the second one here, so we have a pulp and paper mill case study. And for this one, the operators really initially targeted the dryer section and the evaporators individually for those efficiency upgrades. But the local audits identified small savings, but overall steam use really remained high through this process. So when the full mill was analyzed using the pinch methodology, the analysis showed that cross-process integration, for example, using the hot condensate from the evaporator to preheat wash water, was far more effective than optimizing those single units. So the stream demand dropped by 15 to 20% across the facility. And the lesson here we want to drive home is that, pinch analysis is really a whole facility optimization tool, not a unit level one. It's about the network, not just the equipment, okay? And then finally, it's too complicated to get started. So in this case from a refinery, they really assumed pinch analysis was too data heavy and resource intensive to justify for one of their operating sites. But a simple screening level analysis was later performed using the existing operating data that they had. And even with limited data, the team identified multiple feasible retrofit options, including a heat exchanger, rerouting, and preheat train balancing, which is just adjusting which hot streams heat the cold feed and in what order they do that. And this yielded substantial savings and really a short payback. And the lesson here is that, even screening level pinch studies can flag viable opportunities without full-scale modeling, right? So complexity grows only when quantifying those exact design details, okay? And here we have a bit of a reflection. I think this is quite related to what we were already discussing, but we might have misconceptions that affect our decisions to get started with pinch analysis or adopt a more holistic energy approach. I think for the sake of time, if you have sort of a response to this reflection question around how misconceptions might affect decisions within your facility, you can throw that into the chat, but we're going to kind of keep things going because I want to really get into talking about what makes a good candidate. And I think we're going to hear from Emily on some of those criteria and indicators for a good candidate.
Great. Yes, thank you so much, Amanda. So what makes a good candidate, and try and think through your facility while I'm mentioning these key points, and think about if your facility would make a good candidate. So first of all, high heating and cooling demand levels, and high is qualitative. What does that mean? So we do have a few slides later, actual number values that we'll provide to you, and we'll get into those later, but generally high is needed. I would also say it's not listed here really, but constant 24/7 year-round heating, cooling is ideal, because if you're trying to do that heat exchange and either the heat sink or the heat source is not available at different times, you can have like sort of holding tanks that are insulated, et cetera, that could potentially, you know, maybe provide some small buffer, but typically that's not going to work practically, especially with the larger volumes of streams, et cetera. So really, ideally 24/7. I mean, it could potentially work in a 24/5, but you're going to have, you know, that ramp up and ramp down, and you have to use extra utilities during those times as you kind of get to the steady state. So the constant 24/7 is ideal. Multiple process streams at different temperatures. So there's a philosophy in the pinch analysis, which is quite important, which we haven't really mentioned yet, is that, you know, you want to use the highest quality matched with the highest quality kind of thing in terms of your streams. So if you have a cold stream that needs to be heated, you know, from 160 to 180, and you have some high pressure, high temperature steam at, you know, 180, then that would be a good thing to match. You don't want to use the 180 steam to heat from like 30 to 40 degrees Celsius, for example. That would be a waste. That would be not pairing very well. And there's something called a grand composite curve, which we have not mentioned, which is going to help you essentially to pair if you have like low, medium, and high pressure steam. The grand composite curve is going to help you optimize after you've already done the sort of standard composite curves to figure out which of the utilities that you have you should use for which exchange of heat. So again, there's a lot of nuance here behind the scenes. High fuel or steam use, that kind of is probably go hand in hand with the first point, and simultaneous heating and cooling cycles. Again, you want to have that heat transfer happening at the same time, just like the ISO is very cool. I was at the ISO's control room last week and got to see in real time all of how ISO balances the supply and demand of electricity, and they have to do that again in real time. And this is kind of similar here, that you want to be balancing the heating and cooling in real time, and the easiest way to do that is if you have those constant loads. So maybe we can go to the next slide, please, Amanda. So in terms of just some examples, and these by the way are definitely not you know, there's definitely other sectors where this can apply. So these are just some examples. So in pulp and paper, you know, there can be multiple steam levels. By that, again, we mean sort of low, medium, and high pressure, and overlapping heating and cooling between drying, washing, evaporation. So that, as we mentioned, there's a case study in that industry. So that's one where pinch analysis can be used effectively in food processing. And I know we're actually doing a pretty interesting, we're just at the beginning, study of industrial productivity through energy efficiency with I think 6 different participants, including the ISO and others. And we're learning that in Ontario, you know, food and beverage is one of the sort of most, and it was a very important sector from sort of energy efficiency improvement perspective. And we in Thorne Associates do more of the heavy industry, especially mining and steel, et cetera, but we have done some food processing. And anyways, so simultaneously pasteurization and chilling, freezing, cooling can be reasons why the food processing sector can benefit from pinch analysis. And in chemical manufacturing, I would say there's a very strong business case there because they have lots of complex reactions, separation and distillation systems with high heating loads and typically very high temperatures. So that can be an excellent one. On the institutional side, I don't personally have as much experience on this. I know Nawfal does some of his other work, but hospitals simultaneously heating from domestic hot water and sterilization and cooling for air conditioning, for example. In universities, so we have done an energy audit, for example, for York University, and they have natural gas-fired generators, lots of compressors, chillers, et cetera, within their central energy plant, and variable loads across the buildings. The variable loads can actually be not such a good reason for candidate. Again, that constant can be helpful, but certainly that could be potentially something to look into. And similarly with district energy, when you have that network steamed and chill water plants, might be a candidate as well. So with that, I'm going to turn it over to Nawfal to discuss pulp and paper mill case study.
Yes. So yeah, as I mentioned, and also Emily, there was like also a study done like in details and it's published. So I did like many projects through my experience, at least 6 from study to implementation. So yeah, pulp and paper, they are very good candidate for the pinch analysis, and mainly process integration, because they have a lot of losses. They have like so many efficiencies. Many of them, they are old as well. So which making like equipment and processes a little bit inefficient. So if we have to go like through the points, I mean, like there is definitely multiple heating and cooling loops. It's 24/7. So most of the pulp and paper, they are 24/7. So which makes it like a very good candidate for energy efficiency and heat recovery. So there is a from very low temperature, which is like a air makeup, cold water, to the high temperature, up to producing electricity in turbines. And there is always existing energy constraints, and definitely a complex but stable operation. What makes it like complex, it's that there is so many departments. One of the plants had to walk for one mile to get from one end to another, but it is still like it's different plants, so that's why it's like a stable operation. Yeah. So just to make it is yeah.
Yeah, thanks, Nawfal. No, I think this is one of the kind of gold standard examples of a good facility for this. Excellent. So we're gonna now do a quick Menti, because I think we sort of want to know from you specifically on this topic, and maybe Kobe, you can throw the Menti link in the chat again. We want to know, does your facility that you're currently working with have both major heating and cooling systems operating year-round? So you can click the link in the chat. You can also go to menti.com and put in the code. And I'd like to know, you have a couple options here. You can vote for 24/7 and all year round, only for parts of the day. You can, maybe it's seasonally. It looks like we have a couple options, one coming through for seasonally, and then of course maybe you don't have major heating and cooling systems. Maybe and maybe also you're here to just learn more about pinch analysis for your career, your role. It looks like, yeah, we have a couple at least that have sort of 24/7 and all year round, so that potentially make a good candidate here. Excellent. A couple that are more seasonal. Yeah, Emily, do you want to talk a little bit about why maybe seasonally could be a challenge, or maybe just discuss this in general? Yeah.
Yes, exactly. I just wanted to make a comment on the seasonality. So the reason that only seasonally available heating cooling is challenging is mainly on the economics, because essentially the capital cost, you're going to need to have the same capital cost as if it was running 24/7, but you're going to only get the benefits on a seasonal basis. So usually I would say that that's where the economics is going to kind of kill the business case on the seasonality. You may still want to do it if it's very significant, but that's why the sort of more slam dunk is the 24/7 all year round case. And Nawfal, do you want to?
Yeah, I want to add just in some cases, especially in steel and probably mining, sometimes the candidate, it's out of the box. That means it's really an external user. So let's say if you have like a lot of waste, you can valorize it. I mean, like you can convert it to electricity, which either will be sold to the grid or to a neighbor, as well as a steam.
Okay, excellent. Great. So I think we have, Emily, you mentioned a little more detail on this. Maybe we can kind of quickly cover some of these key indicators for if pinch analysis is right for them.
Sure, yes. So high overall energy use, this was the typo, 100, this should say 100,000 gigajoules per year.
Anyway. I think we updated in the workbook, and I thought it was correct on the slide, so maybe it was the other way around. Yeah. Okay.
Yeah.
Good to know.
So,
okay.
Okay. Yeah. So this should say 100,000 gigajoules per year, or 500,000 annual energy cost. So yeah, it just please make sure it is 100,000, just so everybody knows. That's yeah, big difference. Yeah, and both heating and cooling systems operating year-round. We've already talked about that. Multiple process steams with heat exchange potential, and observable waste, again, sort of continuous observable waste through cooling towers, vents, heat rejection could be an indication that that might be a good indicator.
Great.
All right, so I think I'll turn it over to you, Amanda, to go through a workbook activity, or?
Yeah, I think we don't have time to do this live, but we wanted to note, so on page 7 of your workbook, we have created essentially a free screening tool for you to use. Even though we won't kind of pause here for 2 or 3 minutes because we want to definitely keep that time for questions at the end, you can do this sort of as we're going, or you can do this after the workshop or at another time. But essentially, it's just a checklist for you to go through, estimating your sort of annual energy use, identifying some of those major heating and cooling systems you have, sort of counting those number of hot and cold processes as an approximate, and then really noting any signs of potential sort of waste where you have simultaneous heating and cooling or vented heat, cooling towers, etc. So we won't do this within the workshop, but it's yours to sort of take and do with it as you will. And I know there's an opportunity, I think, to check in even after the workshop with Emily and Nawfal as part of this workshop. So I'm sure if you have questions about that, they would welcome them. Yeah, Nawfal.
Yeah, it's very important thing to mention because like many industries, they think sometimes they object the pinch analysis because they think there is no waste. As I showed, or as I mentioned earlier on the ammonia plant. So the savings, that tremendous saving, they were from optimization. It's just doing the same activity, but with less energy. So if there is all this discrepancy of like cooling, heating, there is always a potential, especially like for big consumers.
Great. No, that's great to clarify that for sure. Thank you. Yeah, Emily.
Yeah, and just briefly to build on what Nawfal's saying is risk is also sometimes a barrier, especially in industry, right? If you mess up the process, then it's something is considered high risk, then the operations manager may not want to move forward. But I would say that pinch analysis is very low risk, actually. Usually, you're using indirect heat exchangers. There's no contact between the fluids, and so you're not really changing the process per se. As Nawfal saying, it's the same process. You're just, changing how something's getting heated or cooled, the source, but it should still go from the same, temperature 1 to temperature 2. And so I think that sort of lower risk is an important benefit that perhaps we haven't mentioned previously, and is quite important. We're not introducing any new technology. Like, this is actually not innovative. The pinch analysis has been around a long time. I think the newer software is getting optimized, but I think it's just because it is that complexity is, I would say, probably the biggest barrier. But if you can get beyond that, then there can be some really good savings at, I would say, a lower risk compared to, again, new technology, for example.
Thank you, Emily. Yeah. So I'd love to hear in the chat. You can pop in an answer in the chat to this question. You may have from us going through some of these indicators, some of these signs that you might be a good facility. You may have some sense of this even without fully doing the screening activity yet. Feel free to pop in the chat if you think you might be a good candidate for pinch analysis. Maybe you can say something about what made you say yes or no to this question. So I will continue, but feel free to put that into the chat so that especially Emily and Nawfal have some sense of sort of how many good candidates we have here today. So where do we go from here, right? Especially when we consider that this is a complex thing, and that complexity is one of the big kind of barriers. So we kind of came up with this bit of a 4-step framework, but I do want to say that, this isn't actually meant to be a specific order. Of course, you can follow these in order, but it's really about making these steps kind of work for you based on where you're currently at and your needs. So the first thing we wanted to mention was really around training and capacity building, right? So this idea that you can take introductory or advanced pinch analysis courses, which are available to you to kind of build that capacity within your own team. And then Try. Try is all about, software tools, whether that's free options or paid options, really kind of getting in and starting that screening process using maybe an Excel-based or an open source tool, maybe a licensed tool that you want to invest in to really get that more detailed analysis. And then Scale is all about expert engagement, right? So maybe knowing when to bring in consultants or external specialists that can help you manage through some of that complexity. And then finally, seeking support. So we haven't heard a lot today about maybe resource constraints, but we know that that can be a real barrier or real issue. And I wanted to mention here, especially this is, I think, a critical mention, is that NRCan does have a funding option for this. There is a sort of application and program that you can explore through NRCan. And I'll ask Kobe actually to drop the link for this NRCan funding right into the chat so you all can have that access to it. And I don't know, Emily, maybe I will give you a chance to speak to that funding. Is there anything you wanted to mention about NRCan funding?
Yes, absolutely. Yeah. So NRCan has some process integration study funding, which pinch analysis qualifies under that, and it's up to $40,000, I think 50%. So I think that is definitely, you can essentially reduce the 40,000 off your cost, so that can be great as well. And we have got permission to mention Enbridge as well. So Enbridge also has some funding available, and you can get under the industrial custom engineering program. There's up to 50%, up to $250,000 for custom engineering. That one is less specific. It's not exactly specific to process integration, so you'd need to see if that qualifies directly with Enbridge on your specific sort of case. And obviously, if with Enbridge you have to be using natural gas for your heating, if you're using something else, that's not going to work. But yeah, I would definitely encourage you to reach out to NRCan and Enbridge for funding if you'd like to pursue pinch analysis.
And Kobe, I realized that I think the link was missing from the document, so I've plugged it in myself here into the chat for folks to access. Excellent. So great. So we have a bit of a little case study here. I won't go through this in detail because of time constraints, but I believe this is available in your workbook, and it's just an example that we mocked up to kind of imagine this food processing facility that sort of went through these steps of trying, of scaling, of seeking support, and actually the learning came later, right? They decided to kind of build that internal capacity later on. So again, I won't go through this in detail because definitely want to make sure we save time for questions. There is another workbook activity that you can also do on your own time, and this is a decision tree that you can kind of follow along to really determine what your next steps are, right? What are those steps that you should take? And you can follow along the decision tree to, answer questions looking at maybe you need to learn a bit more, right? You need to understand what this process is all about, in which case, you might want to seek training options. Maybe you need to understand if your facility is a good candidate. Maybe you're not quite sure yet, in which case you might want to use a free or demo screening tool to determine that. Maybe you have a very complex system and you really don't know kind of where to get started, in which case you might want to consult an expert. And maybe you've screened, maybe you know that pinch analysis is the right fit, but maybe you're lacking some resources to getting started. In which case you may want to explore those incentive options. So feel free on page 8 of the workbook to go through this decision tree and sort of chart your own path towards your next steps when it comes to pinch analysis. We have just a few minutes only left in this, but I did want to kind of check in at this stage before we wrap things up, to see if there are any questions for Emily and Nawfal. I do see I think a few things in the chat here that we can look at. I think Matthew has a question around, is 100,000 gigajoules per year the minimum baseline thermal energy input generally required to make the business case favorable? I'm not sure if anyone would like to tackle that, maybe Emily or Nawfal, tackling that minimum baseline thermal energy input.
Yes, I would say that as a rough guideline, that would be correct. So that would be the minimum that you would, and again, it's thermal energy. I see another question.
Yeah, is it thermal energy or the actual energy consumption?
Yeah, so it is just thermal, so not the electricity, unless it's like an electric boiler that you're using for heating, for example. But it would be thermal energy. Yeah.
Great. And then you may have already answered this. I see a comment here. Oh, Nawfal has potentially answered this, but maybe we can discuss a bit more. Is costing process similar to audits, as in audit days, or based on the number of processes? So thinking about costing and complexity, I think Nawfal mentions, per se, since the pinch analysis process integration is a deeper analysis of the processes and touches different systems, it could be more expensive than the energy audit. I don't know, Nawfal, if you want to say any more about that, that specific question.
Yeah, in fact, like energy audit, it's always like touching almost all aspects, including lighting, motors, and so on. So that's why sometimes it can be more expensive. But if you compare an energy audit to pinch analysis, just for the thermal or cooling and heating systems, it should be like more expensive.
Got it. Yeah, Emily, do you want to add?
Yeah, just to add to what Nawfal's saying, yeah, when we price out pinch analysis, we do it based on the number of streams, so hot and cold streams, and we have a confidential, dollar figure associated with that. But yeah, it's not based on audit days, but rather essentially the complexity of the system, because you can imagine that it's the number of hot streams and cold streams that will drive the whole analysis and how complex that is. So.
Yeah. Nawfal, did you have something else to add? I see your hand up. I wasn't sure if that was a mistake.
Oh, sorry. I think it was left there, but
that's okay. No.
Okay.
Just validating. Does anyone have any direct questions? Like, feel free to unmute and ask your question directly. I think we can take probably one more question before we kind of wrap things up. Looks like hopefully we answered most questions, and hopefully people will be rating themselves higher on their knowledge of pinch analysis now. Would be great actually if we did another Menti to see where everyone rated. Okay, great. Yeah, I don't see anything else. Emily, is there any kind of final words you want to say related to any of the questions we've got, or anything that was covered that you feel like we've missed before we wrap things up?
Yeah, I just wanted to emphasize for that in-depth further training. Again, NRCan has that, I think it's a 3-day, or maybe it's actually through SIET now. I think it is actually through SIET. So I've run that training in the past, but now it's a different SIET colleague I've passed that torch on. But yeah, I would encourage you, if you want a deeper dive, or if you don't want to learn any more because you've just and you want to have a consultant again, of course we'd be happy to do that. So feel free to reach out.
Great. Yeah, we have one more Menti question, although we are pretty much at time here, but I guess I'd just like to leave sort of this kind of final reflection as far as, thinking about one action that you might take after this session. So now that you've kind of got this knowledge, you've learned a little bit more about what is pinch analysis, why a holistic and system approach is so valuable. What's one thing that you might kind of do as a next step or takeaway from here? And I already see one response, which is great, which is complete additional training. Yeah, absolutely. This is just an introduction. We're really just hitting the very tip of the iceberg. There's much, I think, under the water here to explore, much more to learn. So that's a very good next step, and I think Emily and Nawfal would also agree. So before we wrap up, just quickly wanted to promote this really great podcast that Save on Energy is doing, the Energy Manager's Playbook. You can feel free to use the QR code to get into that podcast. Maybe listen to it on your way home today if you haven't had enough energy efficiency talk. It's a great resource, and we hear from different energy managers about some of their challenges and successes. Also, really a reminder to stay connected with tools and resources as part of Save on Energy. So lots of good virtual one-on-one coaching like this. There's also a post-webinar support intake form for tailored support for organizations to manage energy resources effectively. We also have a monthly bulletin that you can sign up to receive monthly training updates on all Save on Energy training and support. Also, check out the Save on Energy website for the live training calendar for all upcoming workshops and webinars that are happening. This is a great resource for you just on the Save on Energy website to access all this great material. And just as a heads up, there will be a survey coming out. It will come from surveyinfo@forumresearch.com in the coming weeks. So be sure to keep an eye on your email. And we really benefit from the feedback from you all who participate in the various Save on Energy program elements. So we would highly encourage you to complete that survey. And just wanted to say thank you. Thank you to Emily and Nawfal for your amazing insights. Thank you to Kobe as well, who's helping with production. And obviously, thank you to all of you for coming and for participating, for responding, for your great questions and your attention that we got today. So thank you so much. And we hope you have a wonderful rest of your day.
They said they had two.
Thank you. Thank you, everyone.
Yeah, perfect. Yeah, okay. It's like, I don't know, I lost Matthew. Thanks.
Great. Have a great day, everyone. Thank you so much. Thank you, Devin and Tyler. Have a great day. Okay.
I think I'm going to drop off then, Amanda.
Yeah,
or did you
no
want me to
problem.
stay on? Did you need me to stay on for any?